My name is Radar Bjurhovd. I'm the moderator for this session. I'm a consultant from Tucson, Arizona, where we have had a very beautiful winter, I should say. It's a pleasure here to be here in Nashville and to be at the National Steel Construction Conference. This is my 40th NASCC. It's quite an interesting... Anyway, we have a very interesting topic here, recent developments in design for ponding. And we have two outstanding speakers, Arvind Govardhan from Stanley Lindsay and Associates in Atlanta, and J.R. Miyagits, also from Atlanta with CASE in Atlanta. You are here to listen to the speakers. Let me give you the PDH code for this session. It is 53168. 53168. And I'll repeat it at the end of the presentation as well. So that's the PDH code. And Dr. Govardhan will start the presentation, and then Dr. Miyagits will take over. Arvind.
Thank you, Radar. Good morning. Let's see, PDH code 53168. Let me see if I can go back. I skipped the first slide. Okay, the outline of the presentation will be basic concepts. We're going to look at a historic evolution of the provisions in the AISC, culminating with where we are in AISC 36010. We'll talk briefly about the changes that are in the ballot right now for 360, the year 2016. There are changes coming down in ASC 715 and the 2015 IBC. Thereafter, JR is going to talk about the theoretical basis of the provisions in AISC 36016. He'll briefly discuss the computational approaches and then present some issues with ponding and actual structures. And the last slide is, resources and what we use to present this or prepare this presentation. Starting off with ponding, the first definition is from a roof contractors association point of view. It says that ponding is water that remains on the roof 48 hours after a rain event. That's not the ponding that we're interested in as structural engineers. There are other ponding definitions. One that comes out of the SJI Technical Digest, it starts off with a ponding is a condition where you have uncontrolled water and it changes the assumption of your design. That's not really a very good definition of ponding either. Okay. AISC has a definition that says it's the retention of water solely due to the deflection of the roof. We tend to look at ponding as a process that causes progressively increased deflections that eventually would stabilize, hopefully, or lead to collapse. Okay? And we'll look at the conditions where one occurs versus the other. Just a slide of what ponding looks like. This would be a kind of roof definition where this water stayed more than 48 hours, where it didn't cause any. It represents a condition where the roof got into equilibrium. Basically, the idea of ponding is you have a nominal deflection due to an initial load. Due to that deflection, there's rain that accumulates, rainwater that accumulates. It deflects further. More rain results in more deflection, and the cycle either then stops and it converges, maybe because of a situation where the rain event has stopped, there's not enough water, or the structure is designed in such a manner that the rainwater just overflows. So your input is equal to your output. Graphically, that's represented in these two conditions, where on the slide on the left, the water is overflowing through the scuppers. On the one on the right, the deflections get progressively larger, and the water never reaches the scupper height. And eventually, the deflections become unbearable, or it results in a collapse. There are numerous causes that you can add to why, starting off with clogged drains, inadequate drains. Sometimes ponding is due to an abrupt change in stiffness, okay? And that is the condition that has really caused us to look at these provisions hard again, is that where you have a slope, okay, that comes up against a change in stiffness such that you're coming down a slope, you hit a wall that is unyielding, and you tend to get ponding on the backside of a wall if the members are parallel to the wall that is unyielding. In order to correct that, we go through what our provisions have been in AISC, okay, and how to correct these issues. So we understand that from a ponding perspective, you need a sufficient supply of water, okay, on a flat, flexible roof. Okay? The result of that could either be system stability, where the water inflow is equal to the outflow through the drains, or you have insufficient amount of water, the rain just stops, there was not enough volume of water, and to cause a collapse. Okay? Or on the other side, you have system failure due to an instability or because you don't have sufficient strength. Okay? Some people look at ponding as a serviceability issue in terms of water leaking through the roof and standing water deteriorating roof membranes. That's not the focus of our talk. Neither is the condition of concrete ponding, which also occurs when you're placing concrete on a slab, on a frame slab. As we review the AISC codes, okay, we're just going to focus on what the code or what the provisions say about the mitigation of ponding. I want to think in those terms. What stiffness requirements the code or the provisions impose on us. What strength requirements the codes or provisions impose on us. So as we go through this, think in those three terms. The mitigation, where if there is no accumulation of rainwater, there is no ponding, is one way to look at that. With certain stiffness provisions, you can make sure that there is no ponding. And then with those stiffness conditions, you still have to meet strength conditions that make sure that your beam, your framing system is adequate to handle the loads. So we're going to look at this really quickly through the AISC spec. The first mention of ponding in an AISC spec was in the commentary of the 1961 spec. Okay? And it was a very crude definition. Basically, it said depth of beam or span length to depth of beam should not be less than Fy over 1,000,000. Okay? So you can see the problem with that in terms of a W1416, W1426, W14730, it had the same criteria. Okay? That was not a very good definition. Okay? The other thing in the commentary at that time was that if you had a roof that had a slope of 3 in 12, you didn't need to worry about ponding. Okay? And that was mentioned in the commentary of the 1961 spec. Okay? So taken together, there was a definition of a flat roof, if you read the provisions together, and that flat roof was anything less than 3 and 12. Okay? And if you were a flat roof, then you had to meet that definition of 3 and 12. Just to give you from a historic perspective, that amounted to an L over D of 24 to 30, depending on the yield stress of the steel. The 63 spec came out, and they said, well, Fy over, 1 million wasn't good enough. They came back and said it should be FB over 600,000. Okay? And that is not much better. Okay? It still had the notion of a 3 and 12 roof, okay, to mitigate ponding. If you had 3 and 12, you did not have ponding. The 69 spec resulted in a major change from that thinking, and that is what we have today. Okay? In that decade, there was a lot of research that was done by Hausler, Bohannon and Quincy, Chin, Marino, Moody and Salama, and Sawyer. And JR will go through some of these approaches in detail, but all of them had the notion of a critical stiffness of a simply supported beam, and that was simply the load, gamma being the density of the fluid or liquid, the S, the tributary width, so that gave you a load per foot, L to the power 4th divided by pi to the 4th. That represented an idea of critical stiffness. If the stiffness of the beam was larger than this quantity, you would not fail in an instability of ponding. Okay? If it was less, the potential to have runaway deflections if you had sufficient water is there. Okay? This eventually made it into the spec in 1969, and this is a page from the 1969 spec. C sub P plus 0.9 C sub S is less than 0.25. Let's focus on that. Okay? C sub P are the primary members, S stands for the secondary members. So there's a recognition now that ponding is not just a one-dimensional, one-beam problem, but is a two-dimensional beam, a flat grillage type of problem. There is the notion in the first paragraph that says if you have sufficient slope, okay, but sufficient slope's not defined here anymore, okay, and the idea over here is it says if you don't have sufficient slope, in order to assure stability, that means to get away from instability, you had to meet this equation of C sub P 0.9 C sub S less than 0.25. Okay? You can think of these as flexibility coefficients, okay? And that in the commentary is represented as yielding a factor of safety of 4 against instability due to ponding. So the 0.9 factor on this is not documented anywhere in the literature. It probably represents some stiffening of the beam due to its end conditions or some such condition. You cannot derive this equation just purely on the basis of strength of materials. I have not found the solution to that. If anybody knows of that, I'm asking around. The interesting thing over here is we were looking at stiffness. So the first paragraph has the mitigation aspect of it. The second equation over there has the stiffness characteristics. And that paragraph at the bottom, very bottom, it says the bending stresses need to be no greater than 0.8 Fy. Okay? This was in an era when 0.8 Fy represented something larger than what you would normally design beams for bending, okay? Which was either 0.66 Fy, 0.6 Fy. And again, we'll get into that a little bit later. But that is part of the strength issue is where we are. Okay? So I think I went over these points over here, in keeping that slide up there. Just the only one other thing it mentions very clearly is that you don't need to consider stresses due to seismic and wind events in a ponding check. Okay? So this set of provisions has made it through AISC specs essentially all the way up to now. Okay? There was no definition, like I said, of what sufficient slope was. Okay? In the commentary, the commentary to this reads really awkward, and I stared at this commentary for a long time. And I think that in the committee work, basically it says opposite of what they intended to say. Okay? And you can read it and read it and reread it, and it just says opposite what was intended. Okay? When you have the slides, you can look at that. Okay? They changed the slope from 3 and 12 to flat roofs. Okay? I think it should have said for non-flat roofs over there. There was a provision that was accompanying the provisions in the commentary, okay, that was based on Marino's approach from 1966. Marino was an AISC research engineer at the time, and his method was to be used if the ponding check, the C sub P plus 0.9, C sub S less than 0.25 failed. For most roofs that we design today, it's very difficult to satisfy that and still be economical. Okay? Most roofs fail that test. Okay? And again, Marino is the source for the 0.8 FY, and he just arbitrarily says in his paper that 1.2, it uses factor of safety of 1.25, and that's good enough for ponding in his view. Okay? So that's where that comes. It's inconsistent with the AISC spec, it's inconsistent with the LRFD reliability approach, and that's the way it is. Okay? We'll see how we struggled with it. These were the charts that accompanied that. It was a graphical design aid. It was in the commentary of the 69 spec, and you calculated a stress index, and that's where you see the 0.8 FY. Okay? In either for the primary and the secondary member stress indices. And the procedure is quite clearly described, well described in the commentary. I don't need to go over that. Okay? The issue of why 0.8 FY, okay, I looked hard for that. Okay? And it just seems to be that I'm going to provide a factor of safety of 1.25. It's an abnormal event, and some sort of 1/3 stress increase over 0.6 FY may have yielded the 0.8 FY. We don't know. Okay? There are people in Milbrat, for instance, in 2000 refers to the Marino 0.8 FY as a temporary ponding stress. That could be it. Silver in an AISC article, engineering journal paper says some of the ponding is already accounted in the rain loads, okay, and that's why you can use 0.8 FY or 1.25 stress increase. It could probably be just an inappropriate use of the idea of 1/3 stress increases, which was common. Okay? And there's a paper by Dwayne Ellifret who talks about in that period of time, it seemed to have been very common to have this 1/3 stress increase for abnormal events. The ponding provisions essentially stayed along this when AISC came out with the LRFD spec in 1986. The interesting thing was that Marino's approach, which was a graphical aid, now became part of the main spec. Okay? And as we'll see later on, Marino's example was a very crude, very limiting, filled of assumptions, kind of procedure. Okay? But it is now part of the main AISC spec. The 89 AISC spec that came after the 86 LRFD spec left the graphical procedure in the commentary. It was not part of the main spec. Okay? Just slight implications to that. Okay? The other important distinction was that the changes on the analysis changed from rational analysis to structural analysis. Okay? The assurance of stability became an assurance on adequate strength and stability. Okay? The language regarding checking for 0.89 Fy on the bending stresses went away. Okay? So one would have to assume that the intent was just go back to chapter B, and it says, you know, the resistance needs to or exceed the demand, and I guess that's what they relied on. And no longer did we have any limitation on the bending stress. Okay? The LRFD spec that first came out replaced the 0.8 Fy with phi sub b for bending, which was 0.9 at the time. And the F sub 0 went from calculating for a load case of dead plus R, D plus R, to 1.2 D plus R, 1.2 D plus 1.2 R. Okay? So there's a minor change in that language, and we'll see as the additions have gone that that was an uncomfortable equation right there, and it was changed again. Okay? The 1.2 D plus 1.2 R that was mentioned in the ponding provisions is inconsistent and conflicts with the earlier section of the same spec, where it very clearly said you need to use 1.6 R, okay, based on that. So if we had done it and looked at it properly, we probably would have replaced the F sub 0 term for LRFD in terms of nominal capacity, etc. But it was not done. That's where we are. Okay. The 93 and 99 spec took the phi sub b off, okay, and went to Fy minus F0 for those changes. Okay. There's no indication in the commentary as to why that was done. That's not where it ended. Okay. We'll come to that in a little bit later. BOCA, SBC, the building codes, okay, I went back and looked through what they say about ponding. Okay. And the idea of ponding, the idea of mitigating ponding through a certain slope is always there. The idea of a 1/4 inch per foot evolved after the 60s. And the 1/4 inch per foot would be found in the commentary, but not in the spec. Okay? Until UBC came about in '94, okay, where they defined that if you had a 1/4 inch per foot in the main spec, then you really didn't have to worry, or they said ponding is not required to be checked, very loosely. That was in the same time period. Let's look at ANSI A58.1, which gave us the loads. There were no load cases separate for rain or snow, and live loads included rain and snow. Okay? And we're not very clear what is meant over here, whether the snow, ice, and live combine in one load combination or not. It's not, you cannot make it out. Okay? So, and then you look at those load cases over there. From there, you don't get the 0.8 Fy either. Okay? That was allowed, that was mentioned. So So it's not consistent with the combining of loads, and the commentary to the ANSI document actually very clearly states that a stress increase should not be permitted. The 82 version of A58.1 again says in the commentary, not in the main spec, that if you have a 1/4 inch per foot, you were minimizing the chance of ponding loads. Everybody latched onto that, and typically you saw designs where you had a 1/4 inch per foot and nothing else was done. Okay? The wording is really very poor in terms of the commentary. You read, when you get these slides, you can read through it. It doesn't really tell you much. Okay? The 82 provisions of ANSI were a little bit. There's a remarkable feature in there, is that it required you to consider the rain loads at 1.6 of a load factor of 1.6, but the ponding component, the additional load that you get from the deflection, was to be treated with a load factor of 1.2. Okay? And if you try to do this numerically and you're trying to have the computer do it, this is an extra step that causes a lot of grief. Okay? But subsequent documents that talk about ponding have all gone back to 1.6 as the load factor on rain, okay? On ponding as well. The IBC documents from 2000 on, okay, all picked up on the 1/4 inch per foot, okay, that the UBC started off with. Okay? And the IBC has evolved to a point now in the 2012 edition where you have the notion of susceptible bays, but they are all very clear that if you have a 1/4 inch per foot, that originally in some documents said a 1/4 inch per foot directed to a free edge, you don't have to consider ponding. That directed to a free edge has also gone away in certain documents. Okay? You have to be very careful about that. And a 1/4 inch per foot, we have now seen examples where a 1/4 inch per foot does not preclude ponding. These are all definitions that are from the spec now. They are no longer, so since 94 UBC, the 95 ASC 795, the IBC 2000 onwards, the 1/4 inch per foot is actually not just a recommendation in the commentary, but is a main spec provision. Okay? The interesting thing is that while that is a main spec provision, okay, the commentary on ASC 710, okay, says that regardless of roof slope, ponding instability can occur. So they tell you in the spec that a 1/4 inch per foot will kind of preclude ponding, but the commentary has started moving into the direction of be careful about that. Okay? It's just because there are examples now that show a 1/4 inch per foot is not sufficient to preclude ponding. Okay? Where we are today with AISC 360.05.10 is the same, essentially. It says a roof system shall be investigated through structural analysis if we do not meet this 1/4 inch per foot to a point of free drainage. Okay? This is probably correct except for one condition where the secondary members are probably parallel to the roof edge and there's a change of stiffness in the girdle, okay, direction. The two provisions, the simplified ponding approach, the C sub P plus 0.9 C sub S is called the simplified approach, is in the main spec. The Marino approach, the graphical aid, is in the main spec. Okay? And that, so basically if you look at this, There is a safe harbor in the provisions today of you don't have to check instability due to ponding under certain conditions if you have a 1/4 inch per foot. Okay? That has made itself, again, like I said, in the UBC 94, ASC 795, IBC 2000, AISC 36005, and all documents. It's not just in the commentary of these documents, it's in the main provisions of these documents. Okay? And the AISC provision seems to have allowed for the lower factor of safety or whatever. It's inconsistent with the reliability of the LRFD approach because they have gone back in the 36005 and 36010 documents to the old ASD formulation of that graphical aid, okay, which now explicitly shows the 0.8 FY in those charts. Okay. There are no changes in the IBC 2015 edition that just came out. Okay. There are 2 changes that should be anticipated in the AISC 36016. Okay. One is the removal of the reference to the 1/4 inch per foot slope, okay, as a safe harbor. The other part of it is we've explicitly removed any guidance or any requirement on what those loads are to be used when you use the graphical aids, okay, with a reference that leads you back to the loads that come through ASC 7. Okay. The markup is also included on the slide with what was deleted and what was unfortunately it seems like the strikeout lines don't show on this thing, but what is underlined is new language. What is in red should have been with strikeout. The bottom over there is a clean provision, clean language. And then the changes that's where you see the 0.8 FY has been left in. The provisions read, the provisions given below are to be used, and that has been changed to it shall be permitted because it kind of led you to believe that that's the only way to do it. Okay? So the it shall be permitted to use is you can do it some other way rationally as well. The reference to specific load cases is gone. And now we come to ASC 715. There's a debate going on in that organization to remove the safe harbor against ponding on the 1/4 inch per foot. Okay. They may come back and say it only specifically applies to members that are parallel to the free draining edge. Okay. There is a huge debate going on the term susceptible bay. Okay. And it's gotten, used to be only 2 conditions, now it's about 5 or 6 conditions long. Okay. And there is the notion that engineers are not accounting for the second order effect of the added load due to ponding when they're when they're doing their designs. Okay. So they want to be a little clearer in the notion that ponding results in the R load that you calculate 5.2 times the height of the drain, et cetera, that load actually increases based on the flexibility of your roof framing system. And the ASC 7 committee is seeing where engineers are not accounting for the additional water load. Okay? So they want to be clear about that. In my mind, if there's water being held, there's always the notion of additional load, and you have to check for that. At this point, I'm going to hand over to JR, and he's going to go over the derivation and the mathematics behind the provisions in the code. We'll take questions after his.
Thank you, Arvind. We have a lot of math here, and complete mathematical treatise of everything we're going to talk about is presented here, but we're not going to read every single equation. We're going to try to emphasize the salient points. As Arvind alluded earlier, in the 1960s, there were several studies where people started really thinking numerically about this problem. First came out three sort of independent studies of each other. In 1960s, one was general in nature, one was based on various consideration relative to the wood industry, and then there was another general study, but it was published in the AISC journal by James Chin, who was at the time professor at the University of Colorado, and they dealt with a one-dimensional problem. So basically, this is I wouldn't like you to think about this as methodology. I would like you to think of all of this that we're going to talk about in the next 15, 20 minutes as a numerical solution of a particular problem rather than a method in itself. So and everything you need to understand this is published publicly, but we've provided some of the intermediate computational steps where necessary to understand things. So basically the gist of what all of these guys have done is this. They've taken a simply supported beam. This is a purely one-dimensional problem where there's no participation of the girders or support flexibility of any other kind that would contribute to ponding-induced displacements. So they've taken a simply supported beam. They've described the load. They've described this displaced shape in terms of a half-sine function. That displaced shape in turn describes the load. You simply solve that for mid-span moment, which in turn, in this case, the author used moment area method, which is what derived in 1873 Charles Green. So that's the only methodology here. Any methodology here is about 200 years old. So he basically did undergraduate students' homework here by calculating deflection of a beam. But what he came up with is something that has an intuitive meaning to us. Arvind alluded earlier to the concept of critical stiffness. So if you solve this simple problem, all the computational steps are in there, you will see what's labeled as equation 2 on your right. You will see the summation of deflection due to ponding and the initial deflection, which can be due to any load or even just crookedness of the beam, equals to something that's very commensurate to an amplifier. As we think of how you did second-order analysis 15 or 20 years ago and how you can still do it today under the mandate of Appendix 7. Think about B1 and B2 amplifier. So what you have is an amplifier. If you, in equation 2, move delta sub 0 to the denominator of the left side, so you have delta plus delta 0 divided by delta 0, you have left an amplifier, which is expressed in terms of critical stiffness and actual stiffness of the beam. So I want you to remember this idea of an amplifier. And again, amplifier, the critical stiffness in this case is gamma times L to the 4th power divided by pi to the 4. Okay. Hausler and Quincy and Boynan, and their formulation was slightly different, okay, but it's the same concept. It's what's a derivative of that entire exercise, very simple numerical exercise, is this concept, this notion of critical stiffness. So the idea is if your actual stiffness reaches critical stiffness, you have a runaway deflection because this amplifier that we saw on the previous slide runs to infinity. Again, think about B1 and B2 in Appendix 7, and I purposely named this as B3. All right. It's a one-dimensional problem. It's a very simple thing, and this is still relevant today. If you have an engineering problem such as the one shown on that picture over there, you can still solve a ponding problem using this equation. A couple of years later, maybe a year later after Chin, and there was a discussion published in the AISC journal where somebody pointed out, well, that's all nice, but typical framing applications include support flexibility, in this case, in particular, girders. So how do you account for the flexibility of the girder on the overall ponding behavior? So Marino, who was an engineer with AISC at the time, extended this, again, very particular solution of a very particular problem to what you see on this image. And I'm showing this on purpose because everything that's today in Appendix 2 is based on this very geometry, this very particular specific geometry. So after you go through a simple exercise of defining what your pertinent variables are, so you have an LP as a span of your primary member or a girder, LS is your span of the beam that's framing into it, and assuming that girder supports equal beams on both sides of the bay, that the roof is perfectly plumb and flat, and that beams are sufficiently uniformly distributed so as to meaningfully simulate the distributed load and not point load. You can describe the load condition in terms of deflection for both beam and the girder. One thing to take away from this is that they're codependent. Girder depends, converged loading condition on the girder depends on the displacement of the beam and the other way around. In this entire exercise, now mind you, this was done in the 60s, it was advantageous to describe the displaced shape of the beam as a function of halves, as a half-sign function. Okay, by doing so, the error is, by the way, very small. By doing so, look at the bottom two equations. The one to the right is the simple equation that comes out of Bernoulli-Euler formulation. The one to the left is half-sign function. If you have to numerically manipulate one to the right through various integration steps along the way, it's going to get pretty hairy. Okay, it's a high-degree polynomial. And we'll look later at the differential equation solution in which that thing to the right is nearly impossible to solve during the design constraints. But everything that you see here is somewhat intimidating if you read the paper. However, it's really simple geometry. It's really a geometric problem. And at that, it's really past that the statics problem. But if you integrate the area under that curve, you get 2LD over pi, where D can be either magnitude of your load or magnitude of your displacement, depending on what you're looking at. Okay, and that'll appear in this development over and over again. Okay, what's the error associated with this? I had one of our engineers plot that, less than 2% in the displaced shape if you compare this half-sign curve to the Bernoulli-Euler curve, the derivative of the Bernoulli-Euler curve. Really nothing. If you look at the red and the light blue curve, so that's the second from the bottom, again, they match up pretty nicely. At the initiation of instability for a stability critical system, again, there's about 2% of difference in the critical load. So again, it's nothing. This assumption that you can represent every loading condition by a half-sign diagram is not really correct. It depends, in all cases, it depends what your actual loading is. You just have to think about it. In some cases, if you have a framing configuration that would convey your ponding to your girder through a beam that's very sparsely spaced, you could have conditions where this kind of gets out of hand. Okay. So it's important to think about this rationally. However, if you have uniformly spaced beams, it can actually be shown that it is conservative to represent your girder load as uniformly distributed load on both sides, assuming you have equal beam spacing on both sides, equal beam spans on both sides. It's because you lose this portion of the load, so the resultant winds up being less. Okay. All right. You're going to have a lot of math here. You can go through these slides later. I'm not going to read the equations for you, but I've gone through and derived absolutely everything that's in that paper, so you can follow these computational steps relatively easily. But again, the benefit of using sine pi x over L function is that as you integrate these things, as you find centroids of the area, pi's just keep compounding. Okay, so as you go down the path of determining moments and deflections, your pi's will raise in power, but simplicity of the function remains relatively simple. So if we ascribe that load in terms of geometry of the displaced beam and the geometry of the displaced girder, we go just through the process of doing statics. I mentioned that Chin used moment area method that's derived in 1873. Frank Marino used conjugate beam method, which is, I believe, it was derived in 1865, so this is really old. They didn't have calculators, but this resembles an undergraduate homework. All of us have taken structural analysis. This is one of the things that for some reason they still teach. You can write out the equation of the displaced state of the system. So we've gone through the exercise of numerically showing how to do this for the girder. You can repeat the same process for the beam. We're not going to do that again. But I want you to look at this thing right here, what was identified in red. What's the derivative of all of this? When you remove virtually every constant out of this, what you have here, again, is this concept of critical stiffness. So this is very intuitive. You kind of know what this means, and you can see it from the development of the work. It really has a meaningful physical meaning as this approaches as gamma ls times LP to the fourth power over pi fourth, as that approaches EI. Okay, you have an unstable system. Your deflection will run into infinity. Look at this equation. This is CP as defined by Appendix 2. All right, you've all seen this equation. The start of my career, when I looked at this CP, it's really not intuitive at all. What does that mean? Okay, pretty much nothing the way it's written, but if you look at where it came from, this is pretty intuitive, isn't it? Okay, but the only thing that was done here is that constants were killed off. Back then it was advantageous to remove computational steps. So pi to the 4, 29,000 unit weight of the water was removed. Okay. So you have this constant that's somewhat, I drew a black box around it because it somewhat resembles a black box. It's not really clear what it does, but it kind of resembles something that works that may have been derived experimentally. Nonetheless, but it's this same concept of critical stiffness that keeps appearing through these studies, whether you're working with a one-dimensional, two-dimensional problems. Now, this was done back in the pre-computer era, and what was done then, it was advantageous to fragment your calculations. So if you have an equation that's 20 feet long with 20 terms in the numerator and 25 terms in the denominator, what do? You come up with these intermediate constants to group your terms. So you can compute one thing, plug into your equation, the next thing, and so on. So along the way, from this equation right here that was derived in terms of basic terms of the displaced structure, the following was inserted. And this is just to group your variables. This doesn't really have any clear physical meaning. Okay? But if you substitute all of this in the equation that we just derived for that one particular problem, you will get those two equations. And that's all you need to know to execute a ponding analysis for an elastic structure. Okay. Now let's look at this. Here's this equation again. So you have the equation that defines ponding displacement, the displacement under ponding itself for a beam and for a girder. Girder is to the left, beam is to the right. There's a statement in the commentary that Arvin mentioned earlier, and that statement is related to the simplified criteria in Appendix 2. What that says is that simplified criteria, which is at the very bottom of the page, CP plus 0.9 CS is less than 0.25, contains a margin of safety of 4 against runaway deflection, against instability. It doesn't mention stress at all, just says instability. So it leads to the idea that by providing factor of safety of 4, your stresses will be so, your stiffness will be so high, in turn your stresses will be so low that you will be nowhere near a situation where the strength would control your design. But let's see what you know. Like I said, it's merely mentions stiffness. But how can you assure that you don't get a runaway deflection? Well, it's really simple. You want to make sure these two terms, which are the same for both girder and the beam, they don't run to 0. In which case deflection runs to infinity. So you want to make sure that doesn't happen. So if you set, so you want to make sure that this second term right here doesn't run to 1. Otherwise that'll become 0 and then you have an infinity. All right? So if you rework that, you want to then make sure that this doesn't exceed 4, and then if I want to apply factor of safety to that, let's say 4, just like the commentary says, then I want to make sure this term pi of alpha times alpha S times alpha P does not exceed 1. If I rework all of that algebra, I get this. This is what assures with a factor of safety of 4 that my deflection doesn't run into infinity. However, this last equation is in the spec, and we're not really sure where it comes from. It might have, there was a work by Milbrat in 1999 where he had a similar equation and postulated that part of that's based on consideration of stress, but we couldn't derive it, and we banged our heads for about 10 days over it. Okay, so what do we know about an elastic structure, perfectly elastic structure, but forget about residual stresses, just linearly elastic structure. Any two stresses are directly proportional, ratio of any two stresses is going to be equal to the corresponding ratio of deflections to the corresponding ratio of moments. That's, by definition, elastic structure. So if we know that, and if we were able to write our equations for deflections, and if we adopt this 0.8 Fy as our allowable stress, which Arvind talked about earlier, we can write some kind of a strength criteria, because we can relate our deflections to stresses, and then we can assure that we don't exceed certain margin that was determined by Marino as appropriate in his paper, although we're not really sure as to the source of 0.8 Fy. So the basic concept here is that you have an allowable stress. Think about 1989 specification. You have Fy, then you reduce that to allowable stress. Then you have F0, which is your pre-ponding load, and then you have this margin to play with. And this criteria assures algebraically that you stay within that margin. Okay. These deflection expressions are, however, everything you need to describe this behavior. And I want you again to think about this idea of an amplifier. Again, if you're dealing with a linear elastic structure, you can really use your deflections to, what else? To project your moments as well. You can amplify your zero moment and get a ponded moment. We'll get to that a little later. What are these charts? They're really nothing. They're just graphical aids that relate these deflections that we just talked about to this stress margin that we also just talked about. So if you know CP and CS, you can see whether your stress is okay. Or if you want to max out your stress and you know CP, then you can see what stiffness you need on your beam. And if you know the stiffness of the beam and you want to operate within the stress margin, again, you can determine what stiffness you need on the girder. Nothing more, nothing less. It's just a graphical aid. We looked at the first assumption in this development, which is this sinusoidal shape of the displaced beam and load diagram. But what else did we see here? All beams are uniformly spaced. That went into this analysis. A beam occurs at midspan of the girder. That's how the beam was formulated in there, load on it. All beams have equal flexural stiffness, so there's no stiffness discontinuity, and all girders have equal stiffness. All bases are rectangular. That allows this LS and LP variable usage in this formulation. Furthermore, loads on girders assume it's the same beam length before and after the girder, so all successive bases are exactly the same. Roof deck never reverses the direction, so your girder is always a girder, never a beam. So you don't have a situation where all of a sudden a beam becomes a girder because opposite bay flips the direction. Maximum effects. All maximum effects correspond to the midspan. So if you have something that would throw your load off, initial or otherwise, ponded load or initial load, it may not work for you. Snowdrift, presence of mechanical units, and so on. Loads other than water are uniformly distributed. Water obviously is not, because it correlates to this sinusoidal shape of the displaced diagram, but everything else must be uniform. It's just expressed in PSFs. The structure remains perfectly elastic throughout the process. There's no consideration of residual stresses and how that might chew on your stiffness along the way and increase your displacement and consequently bring you closer to instability. All framing is perfectly flat, including that of the adjacent base. All members are pin connected. Marino makes these qualitative statements about why you could use this methodology for continuous framing as well, but that's neither there nor here. You can actually identify quite a few cases where that doesn't work all that well. There are no axial loads. If you put even a small axial load, remember this is a stability problem. You're trying to avoid a runaway deflection. If you put a little bit of an axial load on a beam, you can accelerate that process a lot further and introduce an additional analysis step in this process. There's no member camber. Strength of beams and girders is limited only by flexural yielding. So think about 1989 spec. FB equals small b equals m over s. All right. So you have an allowable stress, although we don't know the source of 0.8 Fy, it implies that members are not subject to lateral torsional buckling. Okay, so members are such that their strength can be ascribed in terms of 0.6 Fy with some arbitrary stress increase. All frame is orthogonal. There should be no skew members. There are no skew members in this little numerical exercise by Marino. There's no impact of non-structural elements. So if you're sloping your insulation such a way to run the water on a bay or run it away from it, that's really not considered. There's no consideration of any sorts of imperfections. That may not be a big deal because you are applying load in the direction of instability just through initial load, but there are cases where it might be a problem, as we will review a little later. And then all members are prismatic. There are no tapered members. All girders frame into a non-deformable support, a column. A girder cannot frame into a girder, otherwise you have another degree of freedom here to consider. Adjacent bay framing is the same as that of the current bay, otherwise you might have to consider what's the impact of continuity and the water runoff among successive bays. Those are assumptions that went into that little numerical exercise. Okay, so technically, if you don't have that exact same situation, you got something else going on. But that's in Appendix D. Not all of these are unconservative. Some are not. But in any case, it illustrates the point that you can quickly get into trouble unless you think very critically about what you're doing along the way. And as we pointed out a little earlier, Appendix 2 is not as mystic as it appears. It simply exploits the linear relationship between stresses, moments, and displacements in order to help you be within certain stress margin that's commensurate with the previous format of ASD. What are the limitations? I couldn't really call these assumptions, but I'm calling them limitations. Well, it's really incompatible with the current format of the specification. So what used to be ASD was true working stress design. You were working with elastic section properties. You were working with a margin of safety that's at some level below Fy or a stability limit. Nowadays, you don't really have that concept. You have an LRFD solution, and then you have ASD methodology, whose sole purpose is to convert that LRFD solution to an equivalent solution for those that prefer to use ASD load combinations. Okay, so we have this entire notion of allowable stress and elastic section modulus as a measure of defining member capacity that's not really commensurate with the current specification format. Then we're talking about system check here, but what are we checking here? We're just checking members. We're checking members' deflections that we're then relating to moments, ergo stresses. We're not checking connections, additional demands on the connections due to this increased load, which may or may not govern your system. We're not talking about overall system stability, which may be governed if 1.2 depth plus 1.6 rain load govern your design. And we're not talking about member shear or any other bracing design of those members. We're not talking about anything else system related. We're simply evaluating flexural adequacy of the member and stability of the member. If we have, furthermore, more complex loading combination, this all falls apart. If you have a situation where in ASC 7, rain loads are combined in at least one load combination with seismic and wind, although that may not, and it's not likely to govern your design if you put, like I said, an axial load on it, on a beam, and that introduces an additional order of problem. Let's look at some computational approaches. This is a summary of the issues. So we have these two things in the appendix too. All right, one is what we call simplified method. It's this equation that virtually nobody knows where it comes from or what its physical meaning is, and it's certainly not commensurate with what's explained in the commentary. Then we have so-called improved method, and that's the classical Marino method. But I want you again to think about that Marino method as a numerical solution of a particular problem, not a method in itself. How do we handle geometric limitations associated with Appendix 2? What other methods are out there to look at this thing? How do we deal with LRFD, and what would be the best thing for the specification to do in the future? So there are three groups of, I identified sort of three groups of methods. There are these Marino spin-offs. They came after Marino. It's a series of papers of people who felt they should say something about what Marino did. So Sawyer published a paper. He was, I believe, a professor at the University of Auburn at the time, and he accused Marino of not considering crookedness, initial imperfection of the member. So he went through this elaborate exercise, but this illustrates an earlier point. You got these parameters that means absolutely nothing. AP, BP, AS, BS, beta, P, beta, S. They're all intermediate variables used to group your variables. But the equation looks scary, it looks counterintuitive, and if you're looking at it, what's your first instinct? Well, you plug the numbers in and you spit something out, right? But it's really simple. His entire hypothesis is that you know what those are, those initial imperfections. You also know what initial displacement is due to load, and you can relate the two via beta, and therefore you ever so slightly amplify your effects here. Marino responded saying, that doesn't really matter. The study went nowhere, but nonetheless, that concept can be useful if you try to consider camber with some modifications. Salami and Moody had some eigenvalue solutions out there for basically adjusting this. They don't call them CPs and CSs, but basically how to adjust your critical stiffness to accommodate other boundary conditions of the beams. So there are springs, there are perfect fixities, and so on. Carter and Zuo wrote a paper in 1999 where paper was about this fellow right here, Milbrat, and what he proposed, but in the process they put out this equation. Effectively, this sticks to the current format of the specification, but provides a perfectly equivalent solution, LRFD solution, for this load combination. It's simply an exercise of prorating the ASD and LRFD load combinations. All right, still completely incompatible with the current specification format, but that's out there. Milbrad had an attempt to simplify those little pesky graphs that we showed earlier, and he wanted to summarize them into two equations. They sometimes work well, sometimes they don't, but that went nowhere. However, that study is out there. I really like this paper in 2010 by a gentleman named Edward Silver. What he did, he basically unraveled this whole thing, and he said, wait a minute, this is not a method, this is just analysis of a simple problem. See what I can do with this type of analysis, and he tried to really open it to the user, but what it really illustrated, again, it's analysis. You can't codify it because you'd have to write the same criteria for basically an infinite number of problems, and they're all different, and they all have very complex solutions associated with them. There's SJI Technical Digest 3. It's useful. It gives some insight into how do you consider camber. And it'll give you further insight into open web joists, which are also explicitly addressed by the AISC 360 spec and Appendix 2, and it gives you some worked out examples to help you along. I'm going to expedite this ever so slightly now through this process. There are Marino prequels, and these are the studies that we referred to earlier, but I want you to think about this second study here, but the second part of Hausler's study. His study was numerical. He described the beam behavior he described the displaced shape of the beam in terms of Euler-Bernoulli equations, basic principles, and he thought about this carefully, but he threw out an interesting point out there, and it was based on his observation of his numerical problems rather than observing anything out there in the field. Basically, it's as prescriptive of a ponding provision as you can get. If you apply 5 PSF to a roof and you have half-inch deflection, So it's a pure measure of controlling stiffness. You may or may not get ponding problems. Under half an inch, you're probably okay. If you have over 1 inch of deflection, you're probably unstable. How's that for a simple criteria? There are new and other ways of thinking. I'm not going to mention factory mutual other than there's something in there about ponding, but it has to do more with verification of actual slope than it has to do with any particular methodology. There was something going on in Europe in the last 15 days, and one of the most prominent things there is a number of ponding-related failures in Netherlands, in Holland. So, as a result, people started thinking about this problem numerically, just like we did in the 1960s. And all sorts of creative ways of thinking about ponding and solving that problem came about. These three gentlemen, Van Herwijnen and Blauendraad, and then Schouten, they're completely unrelated. One is from Delft, one is from Antwerp University, and the other guy is a consultant. But they have three completely different approaches of dealing with this stuff. They're very commensurate in the outcome, but they represent three independent trains of thought. And what we really like is this Blauendraad analogy. They use an analogy of a piston, hydraulic piston. Okay? And if you drop a restraining plate on a little spring and then you pour water over it, yet you have an outlet that at some point will let your water run out, you will have a rate of loading expressed in terms of displacement, not in terms of time, and then you have the stiffness. Okay. If you have a stable system, those two rates at some point will cross. The displacement will catch up with the loading, or the other way around, as you will. If those stiffnesses are, those rates, the rate and stiffnesses are equal, you have an infinity. They'll never catch up. You can pour water, and at the rate that you pour it, the piston will drop. That's very creative. By the way, that paper is on the internet. It's freely available. You should really read it. And third method, not only does it not follow it, the rates diverge, in which case you have an instability. But from that simple linear relationship, you can define this amplifier. Okay, just a simple relationship of loads, water, presence of water, and displacements. And then if you have a multidimensional problem, you simply define your stiffness. You might decide that your deck matters or it doesn't matter, in which case that term is or is not there. But you can put as many terms as are relevant to your analysis. It's a very simple geometric problem. We've gone through analysis here. Blauendraad and Herwijnen have similar approaches, except one likes to use the half sine cycle to describe his load and his displays diagram. The other guy wants to get away from it, and he wants to convert his half sine to uniform. But anyway, if you convert uniform load block to half sine, you can see that your displacement, both of your displacement and moments are relatively equal. That predicts essentially the same response. But you can then iterate that in terms of initial deflection. If you have a pi, as we've chosen in this exercise, your pi just simply gets compounded, and at some point that the term becomes infinitely small and converges again to this function. But this illustrates mathematically this piston concept that we just talked about. There are a number of physical analogies you can draw to that, but this calculation is relatively simple and intuitive. Okay, and then once you have the amplifier defined, again, you can relate your initial moment, your final moment, and then you have something to work with. Okay, you don't have these two distinct checks. You have moment amplification concept, something you deal with every day in Chapter C. Okay. Let's talk about this LRFD stuff and spec stuff for a while. So this is the basic mandate of Chapter C. I have 10 more minutes, Radar. So look at the general mandate in C1. What is it that you have to do in a structure? You have to consider these 5 things. How you do them, it's up to you. There are multiple ways of doing it. But flexural shear and axial member deformations and other deformations that contribute to displacements of the structure, you must consider them. You must consider second-order effects. Okay, if we have a problem that we analyze using this little Merino gadget that's not in Appendix 2, we kind of do those two things, right? We have some sort of an iterative function there, and so we consider these second-order effects, although ours could be termed even third-order effects because our load changes, not just our effects. Our load and load effects both change with each subsequent iteration. Geometric imperfections, no, we don't do anything like that in Appendix 2 explicitly, although we do have initial load that sort of covers that. Stiffness reductions due to inelasticity and uncertainty in stiffness and strength, no, we don't do any of that. None of that's done. And then all dependent effects shall be calculated at the level of loading corresponding to LRFD load combination or 1.6 times ASD load combinations. We certainly don't do that. So how do you reconcile the fact that you have a stability problem yet you don't address it by the basic specification mandate? Think about Appendix 8, to which I have erroneously earlier referred to as Appendix 7. Think about how you did second-order analysis 20 years ago and how you still can't do it today with these very intuitive amplifiers, B1 and B2, and let's keep that in our head. Let's look at the basic problem with ASD versus LRFD. Why do we have to do this thing where we evaluate all effects at either LRFD load combinations or 1.6 times ASD load combinations, then we convert the results later to ASD by dividing them by 1.6. This is a frame problem, but it's something that we can all relate to. It's because first order response is perfectly linear, second order response, we're talking elastic analysis right now, is nonlinear. So it's very clear that the LRFD level of load at the LRFD level of effect, the ratio of the load will not be the same as the ratio of effects. So in this case, we can express that mathematically by just simply D plus A is not going to be, D plus A divided by C plus B is not going to be proportional, it's not going to be equal to the loads. So effects are not going to be proportional to the loads. Why? Because second effect is nonlinear. So think about Appendix 2, though. We don't kind of do this and we don't consider this. We just do this ASD thing, and then we sort of, there are some attempts in the past to convert it to an equivalent LRFD solution. But let's think about how we do this thing with amplifiers in Chapter C. Let's draw some analogy. So imagine, as we said earlier, the only thing that you need here is definition of deflection, and you have that. And then you can generate your own solution for any custom loadings or custom geometries. But imagine if, as part of Appendix 2, the only thing you had to do is compute a moment demand. And you do so by configuring these amplifiers, which are expressed in terms of ponding and initial deflection. And then an alpha amplifier commensurate with Chapter C could be inserted to force you to use LRFD loads to compute these second-order effects. Okay, so unless our math is wrong, you would associate that with the ponding portion of the effect. The initial effect directly in this equation, and then within the ponding equation, ponding deflection equation itself. This is a Merino, let's call it Merino equation that I've simply rewritten without all these meaningless variables. So it's as simple as that. Okay, simple calculation. And then we are left with this very intuitive critical stability critical stiffness to actual stiffness ratio. And then if you believe that residual stresses are important and that you should somehow or another consider uncertainty in your stiffness, you can also plug in 0.9. All right? That's completely subjective. But what that lets you do is you go to Appendix 2, you compute your required moment, then you just go to Chapter F and find your capacity and see if you're okay. But basically, you're just satisfying this basic specification mandate here. That's all you're doing. How do you deal with AISC Appendix 2 geometric limitations? Well, don't use Appendix 2. But if you have to, always err on the side of lesser stiffness of higher displacement, and of larger initial load. Larger initial load may not be relevant for a system that will converge to a stability, might not be relevant from the standpoint of stability, but it'll be relevant in terms of what your effects are that you compute for checking your strength equations. And there are some examples here. There's no sense in running through it. Well, if your LS parameter is different, your bay is skewed, well, use the largest LS. If your two girders are different, use the one with less stiffness, and so on. But exercise critical judgment. Okay, let's look at this very quickly here. Think about these studies by Chin, by Hausler, by Quincy, Bonahan, and Marino. What they do? They use these classic methods that people learn their undergraduate studies: compute deflections, moment area method, conjugate beam method. And these equations kind of look scary in the papers unless you go through them critically and you just break down how they arrived at what. But let's go back to where all that came from, which is Bernoulli-Euler simple beam equation, something we've all seen in our junior year of our engineering curriculum. So Bernoulli-Euler equation is here, and in short, if you take derivatives of it to the right, you'll eventually get from moment to slope to deflection, and then if you integrate to the right, you'll get to deflections, and if you take derivatives towards left, you'll go to shear to, you go from moment to shear to load. Okay, so let's exploit this a little bit, these relationships. Why is this important? Because you can write an equation with just about any loading condition and any moment condition along the beam based on what's actually present in terms of your load and your stiffness, whether your load is uniform, a function of your length, or whatever else. Okay, so if we write that basic equation here in terms of load, so we have a load function, final load function that includes ponding, then we have initial load function, and mind you, this can be a constant depending on your condition. We have the ponding effect function, and then we have displacement. And again, the ponding this WP over X, function of X would only vary if your bays are non-rectangular and your load varies. Let's say your width of load varies along the span of your beam. But then let's reduce that to a very simple case where W is a constant and constant tributary width to the beam, so WPX is also a constant. You get that basic equation there. Now it becomes a fourth order differential equation. But there are these things nowadays, you have to do this by hand. There's Mathematica. You can plug this in and solve it. So if I just plug that very thing in Mathematica, which I did, I got this general solution. And mind you, the only thing I'm after is my deflection. That's all I need to solve this elastic beam problem. And then if I put some conditions in this general solution, I can get a particular solution, which gets numerically pretty hairy, so I'm not going to show it to you. But if you go to this paper by Silver, he did a very similar thing, and I really admire that work. He actually thought of this critically, but it illustrated you can solve just about any problem using this very basic concept that's 1756, almost 250 years old. What the heck, I'll show you the particular solution, that's it. Anyway, that's not that scary. That actually reduces relatively quickly, but there was just no time to do all of that. Iterative approach. So iterative approach, 11:33, I still have 2 minutes. Yeah. Iterative approach, this is 1 or 2 last slides. You need a couple of things. This describes it graphically. We don't need to really go into a great deal of detail there, but if you believe that you should compute your stability-related effects using factored loads as specification chapter C tells you to do, you can actually apply initial load and then just simply keep track of your deflections, execute steps of analysis. The only thing you need for this is first-order linear elastic analysis. You're just using that program as a bookkeeping tool for your deflections and subsequent loads. That's all you need. You just go from cycle to cycle, take some judgment in how to divide beams, but what you must assure is that your program can handle cumulative deflections from beams and girders, not just beam deflections with reference to its ends. If you can do that, you will very quickly find whether your deflection increments grow or not. If they don't grow, that means you're going to eventually become stable, and once you do, at your very last cycle, you will have loads to work with. That you'll have first of all, deflections computed. You'll have moments. You'll have your shears to design members with. You'll have connection forces. You'll have everything. If you have an office building that has, I don't know, 40 column sticks, 160 beams, would you kind of do this thing really? No, but it's really useful to solve failures, to solve complex problems, to determine what exactly happened. Why aren't there programs to do this? Because there aren't programs that can, there are programs that can impose equilibrium on the display shape, but there are no programs, to my knowledge, that will also iterate loads. Okay. So they'll give you load effects on the basis of display shapes, but not loads. That's the basic problem. We don't have time to run through this. These are some notes on, but you will get these slides. These are some notes on how often these failures are. I will just say this. The ideas on this are all over the place. There are people who say, well, this really never happens. There are those that say, well, it happens all the time. And there are those that say, well, it happens in this region under this condition. One last thought, which is this. One thought. What we came away from reading with reading these studies is that if you have a ponding failure, it seems that there's generally some other underlying condition where ponding then becomes a contributing factor rather than the sole cause. Okay. I'll leave it at that. There are some other slides here, but we don't have time for that.
Thank you very much.
Yeah.
I'm sure you have a lot of questions. Questions? Mr. West, please.
Thank you. We don't need this necessarily, but are the codes and standards writers raising any flags about green growths?
About green what?
Green growths. That's the roof that's all the plants where the supporters say that it doesn't affect the roof.
I'm not going to go there.
No, it's an engineering problem.
Sure.
Any thoughts?
No.
Okay. Well, how about the speakers?
Any thoughts on that?
The ponding problem, if you're just talking about accumulation of water, the characteristic of that roof is that it is a very light self-weight. Okay? When you're talking about a green roof, there are provisions being thought about and standards being written for green roofs. The general ponding problem does not manifest itself because the initial dead load is quite large. Okay? And then you take the idea of 1.4 dead, that 0.4 dead contributes to actually a larger amount of water that can be held on that roof. Okay? So there are benefits to designing a roof that has a 100-pound dead weight compared to a roof that is designed only for 10 pounds or 8 pounds a square foot. But going back to your problem, there are provisions being written for green roofs that give you the idea of where you can plant and whether live loads apply to these areas where you're planting, et cetera, et cetera, et cetera. Those concepts are being worked out right now.
Thank you.
You should look at some of the very old structures in Scandinavia, Norway in particular, where they in fact planted grass on the roofs of buildings because they expected cows to go on the roof. And they did.
Yeah, of course. Heidi was leading her goats.
No, Heidi was in Switzerland.
I know that.
Anyway, yes, these are tricky questions. Any other questions, comments? Thank you very much.